Hello everyone, myself Dr. Naveen Kumar R. I'm Assistant Professor in Department of Electronics, MS Ramaya College of Arts and Science and Commerce, Bangalore. So today I'm giving a lecture on combinational circuits, Unit 2 from Bangalore University Electronics syllabus under the course Digital Electronics and Verilog. So in digital electronics, today I'm explaining only combinational logic circuits. So in this topic, I'm going to cover the concepts of combinational circuits, that is types of combinational circuits, that is adder, subtractor, a 2-bit comparator, a encoder, especially the decimal to BCD, and decoder of 2 to 4, 3 to 8 decoder, and BCD to decimal decoder, and multiplexer to demultiplexer, and digital to analog converters, and analog to digital converter. So first we need to discuss the basic concept of a combinational logic circuits. As we discussed in the unit 1, the basic fundamentals of Boolean algebra and logic Boolean function simplifications and K-map constructions. So this is an extended version of that Boolean algebra, that is we are constructing the logic circuits based on requirement of an applications. So combinational circuit is a combination of logic gates, basic building blocks of digital circuits, to implement a required applications. So therefore combinational circuits, we can define it, the present outputs of the circuit or a logic circuit depends upon the present input. Such a logic circuits we call it as combinational logic circuits. Here based on different applications, different combinational circuits we can construct. So that is in order to perform an arithmetic and logical functions, we are using adder, subtractor, comparator and PLDs. And for data transmission applications, we can implement multiplexer, demultiplexer, encoder, decoder. And for code converters, some binary number systems will be converted to another form of the number system, that is binary to BCD, BCD to 7 segment. Different codes can be converted by using the combinational logic circuits. So first we will discuss adder and subtractor. In order to perform the addition operation in binary system, we are constructing a small part of a circuit, combinational circuit, that is an off adder. Off adder, that means it will perform the logical addition operation. Logical addition operation, that indicates by adding, here the two variables I will select, that is A and B. So A is the first variable and B is the second variable. I am going to add these two variables, that is A and B are the inputs. So these two inputs I am going to add, that is combination of the two inputs 0 0 0 1 1 0 1 1. So 0 0, by adding these two in binary system will get the 0 result, that is sum is represented with a S and carry is represented with a 0. And 0 0 output is 0, and for 0 1, 0 plus 1 it is 1, carry is 0, 1 plus 0 it is 1, carry is 0, but 1 plus 1, that is 0, 1 is the carry. So carry will generated, so that carry will be represented as a C. So next, this is a function of an off adder. It will add the two variable by using these expression, that is sum and carry expression. We need to write the uh, boolean expression, that is s is equal to a bar b plus a b bar. It is nothing but XOR operation, therefore we requires one XOR gate. Okay, and c carry, it is logically high only when a and b are high, therefore one AND gate is enough to construct the carry. So for two gates, that is one XOR and one AND gate with the two inputs and two outputs. Similarly, in order to add three input bits, we requires performing the same operation, that is addition operation. 0 plus 0 plus 0, the sum is 0 and carry is 0. And for 0 plus 0 plus 1, the sum is 1, carry is 0. So for this sum and carry expression, we can construct the circuit which requires 4 AND gate, 1 XOR, 1 OR gate for sum, and for 3 AND gate and 1 OR gate for carry circuit. And off subtractor. Off subtractor has like off adder. Off subtractor will subtract the two variable inputs, that is a and b. If it is 0 and 0 minus 0, it is 0, and there is no chances of a borrow. Two inputs and two outputs are there, that is difference is nothing but difference between a and b. And borrow, if any borrow is required, the borrow will be generated. If it is the a variable is 0 and b variable is 1, we are going to subtract 1 by 0. We requires one borrow, therefore borrow is get enabled. It will be represented with the logic state 1, and difference is also 1, because if a variable get a borrow, it will become 2, and b variable, now we are going to subtract 2 minus 1, the difference is 1 and the borrow is 1. So in next case, a is 1, b is 0. 1 minus 0, the difference as usual we know that it is 1 and borrow is 0. 1 minus 1, it is 0 and borrow is also 0. So far, in order to get the difference operation, that is status is difference is 0 1 1 0, it's just like as same as XOR gate operation, therefore we need one XOR gate. And for b naught, it's not only requires only an AND gate, it requires one more NOT gate, that is b naught, one more NOT gate to the AND gate. It will be, we can construct off subtractor and full subtractor. So for 3-bit input variable, same difference and borrow will be there. So for their expression, we need to construct the circuit same as like adder, full adder. And the next circuit is the comparator. So comparator is the digital comparator's purpose is to compare the numbers and represent their relationship with each other. Here is the two variable I will select. So one variable with the 2 bits, that is a is with the 2 bits, that is a0 and a1. So a0 and a1 with the 2 bits, that is 0 0 is nothing but 0, that is a0 is 0, a1 is 0, lsb is a0, msb is a1. So by both the 2 bits will represent the one decimal value. So 0 is 0 is nothing but 0 0 0 in decimal, and 0 1 is nothing but 1 in decimal, and 1 0 is nothing but 2 in a decimal, 1 1 is nothing but a 3 in a decimal. That is maximum 2-bit value, because 2-bit combination you will have four maximum value 0 to 3, that is 0 0 is nothing but 0, 0 1 is 1, 1 0 is 2, and 1 1 is 3. So different combinations of A0 and A1 is represented here, and also the B0 and B1 is as like same A0 and A1. It is also 2-bit pattern of B variable. Now I am going to compare the status of A and B, that is relation between A and B, that is A is greater than B. If A variable is greater than B, then only the logic symbol will get high, otherwise it is in logic 0. For next state, A is less than B. If the A variable value is lesser than the B variable, then it will become logical high, otherwise it will keep it in logic 0. And if A is equal to B, that is if A variable value is equals to B variable, then only it will be logic high, otherwise it is 0. So comparator, a relation we are going to compare, three relation we are going to construct the truth table. So according to this truth table, we are going to construct the circuit and reduce it by using K-map, and we'll get the final expression. So here the three final expressions are there. By these three final expressions, we came to know how many AND gate, OR gate, XOR gates is required. So based on that, we are going to construct the this 2-bit comparator circuit. It requires nearly 6 AND gates, not 7 and 8 AND gates, and 3 OR gates, and 2 XOR gates, and 4 NOT gate. By using this, you can construct the circuit of 2-bit comparator. Next, one more important concept, that is encoder and decoders. So this type of combinational circuit we are using in transmitters and receivers. So encoders will be fixed in translators and decoders will be fixed in receiver part. In between that, some channel will be there. So once we'll encode the information in a transmitter, we'll transmit it through channel, and that received information will again decode it in the receiver section by a decoder. So therefore encoder, encoder is a combinational circuit which converts some encoded information, that is it will encodes the input binary information into a certain single output or a limited outputs. And the decoder is a digital combinational circuit which will gives a limited output into limited input into maximum output, vice versa operation of encoder. Let us discuss in brief with the encoder. So encoder is a combinational circuit that encodes maximum of 2 to the power of n input lines into n output lines. So 2 to the power of, that means maximum inputs, many inputs into limited outputs with one enable line, we call it as an encoder. So here is an example of an encoder, that is decimal to BCD priority encoder. That means many inputs are there, that is D0 to D9. The inputs are 10 inputs because decimal value you can represent with a D0 to D9. Only one decimal value we need to represent with the 4 different outputs: Y0, Y1, Y2 and Y3. So decimal value 1 is represented with the output value, no need to represent it, okay. And the decimal value of D1 is represented with Y0, and decimal value of 2 is represented with y1. Likewise, the different output combination, for different output combination you will get the inputs, that is decimal input values. So for this truth table we are going to construct uh, by using the k-map reduction, or we can directly write the y0 output wherever the d0 input is high. So there we can write y0 output as d1 plus d3 plus d5 plus d7 plus d9. So simple 4 OR gate is enough to construct the decimal to BCD priority encoder. So priority encoder we need to mention here as a priority. So priority encoder is a special type of encoders, because decimal to BCD encoder, what we discussed the truth table, that is right. But in priority is need to given here, it is not mentioned, but priority one extra line we need to specify and connect to these OR gates. So that priority will gives a preferences for a particular output. If you want a particular output having some significance, so we need to give priority for y0, priority for y2. Likewise, we need to give a particular period output, we can get it with one priority control line. And reverse operation of that encoder, that is decoder. The name decoder means to translate the coded information from one format into another. So binary decoder transforms n binary input signals into an equivalent code using 2 to the power of n outputs. Here is a 2 to 4 binary decoder. So in block diagram, two inputs are there, A and B, with the outputs, that is n inputs and 2 to the power of n output. If it is 2 input, 2 to the power of 2, 4 outputs. So Q0, Q1, Q2, Q3. So according to the combination of inputs, 0 0 Q1 is output, and 0 1 Q1 is output, 1 0 Q2 is output. For combination of 1 1 Q3 is output. So by using this truth table, you will get expression for Q0 as A bar B bar, and for Q1 A bar B, and for Q2 A B bar, and for Q3 and AB. So by this logical expression, you can understand how many gates are required. That is 4 AND gates is enough to construct, and 2 NOT gates in order to get the complementary inputs. So by using this expression, we are going to construct the 2 to 4 binary decoder. So as like 2 to 4, 3 to 8 binary decoder has 3 inputs, 1 enable pin, and 8 outputs are there, D0 to D7. Here y0 is mentioned as y, output as mentioned as y0, nothing but a D0. So A, B, C are the inputs, and y0 to y7 are the outputs. So this can be here in this truth table we are using negative logics. Negative logic means the logic high is represented with symbol 0. Therefore y0 is represented as a 0 is nothing but it has the logical high value. So remaining all is keep it as a 1. So similarly y0, y1, y2, y3 is gets enabled with a different combination of A, B, C. So here is output expression by using the above table. Y0 is enabled or logic high only when A, B, C is 0 0 condition. So likewise you will get y1, y2, y3, y4, y6 up to y7 different expression. So based on this boolean expression, we came to know that how many NAND gates is required. Because we are constructing negative logic, we can represent it with NAND gate. And another one more type, BCD to decimal decoder, because we discussed before in encoder decimal to BCD, that is 10 inputs to 4 output. Here it is a reverse operation, that is 4 inputs and 10 output. As like the 3 to 8, here the 4 inputs are there, A, B, C, D, and one enable pin, and D0 to D9 or Y0 to Y9 outputs. That is 10 different output combination. It is also in negative logic. It is represented the output with this logic 0. So for 0 0 0 condition, Y0 is gets enabled, and for 0 0 0 1, Y1 is gets enabled. Likewise, 1 0 0 1 is a last input case, so during that Y9 is gets enabled. So for that, here is a logical expression by using the truth table and convert that truth table into the logic circuits Y0 to Y9 outputs. So BCD to 7 segment decoder. This is a special application in a decoder. Here we are going to represent the BCD numbers on a 7 segments. So 7 segment decoder is nothing but a 7 segment display is a type of a display devices. So in that two variant you will get common anode and common cathode. So in common anode, the anodes will make it as a common, and it is explained in the notes. You can go through with the supplementary files provided below. So there common anode and common cathode circuit. In common cathode, the cathode terminals of the diode will make it as a common. In common anode method, the anode terminals of the diodes will be make it as common. So here is 7 segments, 7 LEDs are arranged as shown in this figure. That is A, B, C. It is arranged A diode or A LED, B LED, C LED, D LED, E LED, F LED, and G LED in this arrangement. So in this arrangement, in order to represent logic 1, we need to enable or turn on the LED of B and C. In order to represent the digital BCD 0, we need to turn on A, B, C, D, E, F. Okay. In order to here, we are going to construct the BCD input, that 4 combination of BCD input represented with pattern. Here the output is represented with A, B, C, D, E, F, G. So in order to represent 0 combination, all the LEDs A, B, C, D, E, F LEDs need to get turned on except G output or G LED. So then only we can visible that the 0 BCD 0 in the display devices. Likewise, in order to represent 1, B and C we need to enable, remaining all keep it as a off condition. So by providing suitable logical inputs to the display devices, we can display the BCD values by blinking particular LEDs. And one more concept, important concept in combinational circuit, that is multiplexer and demultiplexer. So as like encoder and decoder, multiplexer will also acts as a that is multiplexer is receives 2 power of n number of inputs into n number of outputs. But one more control signal is exist in multiplexer, that is selection line. So based on selection line only, it will receive the particular inputs and it will allow that input to flows through that circuit as an output. So that is a major role of multiplexer. And demultiplexer converse of multiplexer operation or reverse operation of multiplexer, that is n number of output will be input will be converted into 2 power of n output with respect to the given selection line. Let us discuss the multiplexer. So multiplexer is a combinational circuit that has a maximum of 2 to the power of n data inputs and n selection lines and single output line. It has only one output state. Either any one input will be flows through or reflect as a output based on the combination of selection line. So one of these data inputs may be connected to the output based on the value of selection line. Here is a 4 to 1 multiplexer. So 4 to 1 multiplexer truth table. Here it was given, and a block diagram. I0 to I3 will be the inputs, different inputs. Y is an output. So output will reflect any one input based on the selection line combination. Therefore selection line combination. So Y you will get I0, I1, I2, I3 at different conditions of selection line. If selection line is combination is 0 0, I0 will be the output as a Y. If it is 0 1, I1 with the output, 1 0, I2 with the output, 1 1, I3 will be the output. So based on this expression, we are going to construct the circuit. It requires 2 NOT gate, 4 AND gate and 1 OR gate. So demultiplexer, a reverse operation of the multiplexer, it has 2 power of n number of outputs with n number of selection lines. If it is a 4 number of output, the selection line will be n at 2 and input is only one single line. So here is also the selection line 0 0 combination. You will get the 4, that is y0 will be the output, and if the selection line is 0 1 0 0 1, you will get the output of y1, and if it is 1 0, you will get the output y2, and if it is 1 1, the output is y3. So by using the truth table, we will get an expression. So based on this expression, we are going to construct this multiplexer circuit. So that is about combinational circuit. So next important concept is that is digital to analog converter, digital to analog converter and analog to digital converters. So these two converters plays a very major role in communication system, because each physical phenomenon which are occur around us, we can't able to trace it out and we can't able to process it through a machines. So therefore we require some converters which converts the physical phenomenons, because those things which are appeared in analog form, we can't able, because it is a continuous process, we can't able to process through directly to the machine. Therefore we require some converter. So first we discuss digital to analog converter, that is machine to external uh, physical phenomenon. That means display devices and different things are uh, digital devices, but they will display the information that can be easily visible by our bare eyes. So that can be possible by using this kind of devices, that is digital to analog converter, which converts the digital input signals into an analog output signals. So digital signal is represented with a binary code, which is a combination of bits 0 and 1. The different variants will be available in digital to analog converter, that is a binary weighted resistor DAC and R to 2R DAC are the two variants available. So shall we discuss the binary weighted resistor DAC? A weighted resistor DAC produces an analog output which is almost equal to the digital input by using binary weighted resistor. In the inverting adder circuit, in short, a binary weighted resistor DAC, we may also call it as a weighted resistor DAC. It has one inverting operational amplifier. So for that inverting amplifier, we are connecting the three binary weighted inputs, that is B0, B1 and B2 is a switch. So it is connected to the positive supply, and it is connected to with a weighted resistors weighted resistance of 2 to the power of 0 R, 2 to the power of 1 R and 2 to the power of 2 R, nothing but 4 R, 2 R and R. So those binary weighted inputs are provided to a inverting amplifier. We have an expression for an output before a feedback circuit, that is inverting, that is V0 is VR of, that is a reference voltage with respect to the feedback resistance and common R value, and binary weights B2 by 2 naught 2 to the power of 0 plus B1 is divided by 2 to the power of 1 plus B0 with the 2 to the power of 2. By substituting R is equal to 2 RF, because we are giving the feedback resistance, R value is equal to 2 of RF. At last we will get a final expression V0 as a V reference divided by 2 with the B2 by 2 raised 2 plus B1 by 2 raised 1 plus B0 by 2 raised 2. And what are the disadvantages in binary weighted DAC? The difference between the resistance value corresponding to LSB and MSB will be increased as the number of bits represented in the digital input increases. And it is difficult to design more accurate resistors as the number of bits representation in the digital input increases. Therefore, in binary weighted, it is difficult to difference between the LSB and MSBs, and we can't able to fetch the accurate value of analog input by using this binary weighted resistor type DAC. So in order to overcome that, we are using R to 2R ladder circuit, same as like binary weighted resistors. Here we are using some ladder circuit of R to 2R, that is R to 2R ladder is a DAC overcomes the disadvantages. It has analog outputs which is almost equal to a digital binary inputs by using R to 2R ladder network in inverting adder circuit. Depending upon the status of the bits B1, that is B0, B1, B2, we are providing a different binary inputs, that is 0 0 0 0. So digital value as a 0 and 1. So based on this digital value, it will converts into the output voltage by using this formula V out is equal to minus V reference, because this is same as that we are obtained in binary weighted resistor formula. By using this formula, you will get the different V out voltage from 0 to minus 1.75 variant. So next concept is analog to digital converter. Analog to digital converter is a reverse operation of D to A converter. So A to D converter, which device that converts analog signals, usually voltages obtained from the environment or physical phenomenon, into a digital formats. That means a human eyes can, it's a continuous process, or analog signal. It can analyze only an analog signal. It is difficult to understand the digital information by our eyes. Therefore, we are designed display devices or a mobile screens. So those are analog output. but that analog output will convert into a digital form during process inside a machine. For example, a mobile phone. So the information which is visible on the display device is in analog form, but your system can't understand this analog information. Therefore that analog information will be converted into a digital inside the mobile phone by using some processors. After processing the digital information, because a user can require some operation. For example, I will touch the mobile phone screen, so it will response for my touch. That means the biopotentials analog signals is converted into digital information. So digital informations will uh, process the user information, and again it will converts the digital information into analog information and displayed it on the screen. So in that case, the analog to digital and digital to analog converters is very significant. So in conversion, during analog to digital conversion, it requires some uh, importance or take care about sampling, quantization and coding process. So quantization process is nothing but we are sample the input continuous signals with the some time intervals, and we are round up the values to a certain nearby values, make it some stairs. So that is nothing but a quantization. And different types of analog to digital converters exist in ADC, but successive approximation is the most common analog to digital converter used in several applications. So successive approximation is a ADC which converts analog signals to digital by using binary search algorithm for a comparison process. Here is a block diagram of successive approximation ADC, which has one VA analog reference input voltage and with comparator. So that means the previous values, that is successive approximation, will perform the binary search and it will sense MSB, that is analog voltage will be converted into MSB and LSB, and one more comparator, that means the digital output will continuously compared with the V in by using a comparator. So here is a binary search algorithm which follows the three major conditions. If MSB is 1, the circuit gets on. If the reference input VA is greater than VD, set the next bit from the reference bit. If VA is less than VD, set the bit will get reset and set the next bit, that is VA is equal to in this tree I am representing VA as nothing but a V in. So now V in is now 3 volts. So 3 volt is nothing but binary representation as 100, 3 bit combination. So if V in is greater than VD, then the set bit is now 1, that is MSB. Now the set bit is this one 1, and this one, if V in is greater than VD, the next bit, this bit will get set and the binary pattern will become 110. If it is V in is less than VD, that set bit is become 0, the next bit will become set and the binary pattern will become 010. So this tree will continue for all the 3 clock cycles. At last you will get all the patterns of the different binary patterns, that is 00 to 111.